Welcome to Learn with Izhar. I'm Sheikh Izhar, your host with over 28 years of global software development experience, building large-scale intelligence systems for enterprises in logistics, aviation, telecom, and fintech. Today, we are diving into a problem that every logistics company, courier platform, and supply chain operator faces daily. How do you optimize delivery routes dynamically in real time while considering variables like traffic, fuel, weather, and constraints like delivery windows? We are going beyond static rule planning and exploring how deep information learning is revolutionizing route optimization. So, what are traditional route optimization? There are certain limitations associated with them. Most logistics firms still use static route optimization algorithms like Dijkstra's algorithm, A** for shortest path, Google OR tools for TSP, traveling salesman problem. While useful, they assume a fixed step, fixed plan, no dynamic changes, predefined objectives. But the real world is dynamic. Roads get blocked, traffic patterns shift, customers cancel, new deliveries arrive as well. So this is where reinforcement learning, RL, steps in. So why deep reinforcement learning? Deep reinforcement learning, DRL, mimics how humans learn from environment and reward feedback. In logistics, the environment is your delivery map, real-time condition, and packages. The agent is your routing engine, and the action is choosing the next delivery node. And what's the reward? It's minimizing time, distance, fuel, or maximizing customer satisfaction. Over time, the agent learns to adaptively plan the most efficient route, considering non-deterministic elements like weather changes, road closures, real-time fuel consumption, vehicle load constraints. Enables self-improving delivery models that adjust in real time. So what are the core technicalities involved? Let's break down the core RL components. First of all, is Markov decision process, which is generally known as MDP. It states delivery status, location, weather, and traffic. Also, the actions involved move to next delivery node and rewards ultimately time cost savings, successful delivery. There are certain transitions involved, which are actually state changes after each action. Also, we need to have deep queue networks, DQN, which is useful for discrete action spaces. For example, choosing among limited routes. Neural network approximates queue values for state action pairs. Also, it trains using replay buffer and Bellman equation. Another important idea is related to Actor-Critic models, which combines policy gradient, actor, and value function critic, which is suitable for continuous and hybrid decisions, speed and time windows, more stable and sample efficient than vanilla DQM. Then we have got graph theory, in which delivery zones are models as graphs. RL agents learn to traverse the graph dynamically. They can embed GNN graph neural networks for richer edge and node information. So how we implement all those concepts practically through the practical implementation pipeline. So let's talk real-world architecture. First of all, we need to set up environment simulation. We need to use OpenAI Gym or custom environments that simulate delivery scenarios, which includes traffic simulations based on APIs like Google Maps or here. Also, weather data from OpenWeatherMap and dynamic order insertion. Then we should have reinforcement learning framework. Maybe we can use RLlib, which is scalable RL with support for DQN, PPO, A3C, and more. Also, we need to define observation space, route context, ETA, and traffic load. So, action space, which is next delivery point, and the reward function, which is fuel usage, latency penalty, SLA compliance. And after that, we need to set up optimization baseline. We can use Google OR tools as baseline TSP VRP engine for comparison. It can be hybridized with RL to form start route plans. And data handling is very important here as well. We need to store training data using tools like Apache Parquet or Postgres in order to enable offline replay and tuning. And ultimately, continuous learning. We need to retrain models weekly using real delivery logs and also use online learning for active route tweaking. Let's discuss a use case related to a retail logistics company. Let's say a last mile delivery service in a metropolitan city handles 1,000 packages per day with 50 vehicles. By using deep RL, they reduce average delivery time by 18% and also improve fuel efficiency by 12% and handle unexpected traffic 50% better than rule-based routing. So what's the solution? The solution involves trained DQN agents on city map graphs, which use live traffic APIs to update environment, and also reverse penalized late deliveries and fuel overuse. It's deployed on Edge using Onyx runtime to run models on mobile driver apps. There are certain best practices and takeaways which we need to keep in mind while implementing similar solutions. First of all, hybrid approach wins. Combine traditional route planners with RL agents for fallback and benchmarking. Also, model interpretability is important. You need to explain why a certain route was chosen. Helps gain trust from ops teams. Also, multi-agent systems should be there. Fleet level optimizing. Using multi-agent RL, agents collaborate, not just act in isolation. We need to have a cloud-native deployment. Deploy models on AWS Lambda or GCP Cloud Functions for real-time interference. And ultimately, compliance and safety is very important. We need to ensure all dynamic routing as respects regulatory boundaries, i.e. vehicle type restrictions, delivery hours, etc. And that's how deep enforcement learning is transforming the future of logistics with a smarter, adaptable, and efficient route optimization. If you are working in supply chain, last mile delivery, or mobility, this is not just innovation, it's survival. Subscribe to Learn with Izar, where we turn deep tech into real-world impact. Comments below if you'd like a full step-by-step implementation video. using RLlib and OR tools. Thank you and have a nice time.